All right, everyone. Welcome to our seminar today by Tristan Lawrie from the University of Nottingham. Tristan joined the programme last week, and he's almost to the end, correct? I haven't been to one of these seminars yet, but I warned him that people like to interrupt and ask questions. He is quite happy with that and will do crowd control as necessary. And he realises that he wants coffee, something. So, Tristan, over to you. Feel free to give us a more introduction than that.
Okay, yeah. I'm from Gaussian University. I'm in my final year of my PhD, and I'm going to present some work I did over the last few years, a quantum graph approach to metamaterial design. And I should say this is supervised by Gregor Tanner, Gabriele Guardoni, Demetrios Chronopoulos, and I've done some related work with Sven Grutzman as well. And so I'm going to give you a very, very patronizing introduction of what a metamaterial is. I know everybody knows a lot about it already, but it just means beyond material, where we have some structure here, which is constructed of a set of, in this case, periodic resonant elements, but those resonant elements are typically smaller than the size of the wavelength of a probing wave. And what that allows you to do is, in some frequency regime, is to give rise to some non-trivial wave dynamics. And so, for example, there's this I think, maybe the holy grail of metamaterials is to say, imagine an incident wave coming in from the left, plane wave, and an incident wave coming out from the right. I should be able to, in this white region, put some object, and by arranging these resonant elements around that object, I should be able to guide the field of the wave around the object and completely reconstruct it the other side without having perturbed the field. And if you were to stand the other side of this, you would have no knowledge that the object was there. However, this is solved in the continuum. You do some coordinate transformation, and you can show that how the refractive index of, in this case, light should change as you move through this object. But that doesn't tell you anything about the underlying structure, this metamaterial structure of these resonant elements. And there is a disconnect between those two worlds, where I have an understanding of resonant elements, I can construct them in some mesh, and then if you solve that problem, you can recreate the continuum solutions, but it doesn't seem to be the case that you can do it trivially the other way around. These inverse problems are a great area of research. And so what I want to do is just, I've stolen this from David R. Smith, but I really love it. I think it's a really good diagram that explains the two different domains as a function of wavelength. If I think, first of all, let's think in this wavelength, in this long wavelength regime, of course, the wave has absolutely no knowledge of the underlying structure, and so you see this sort of continuous domain, and you can get things out of it like Snell's law, where I say there's one refractive index that describes air, one refractive index that describes say a crystal, and then I can shine my light into that object, and I can see that it refracts by some amount. Okay? But as I move down shorter and shorter wavelengths, where the wavelengths then become of the order of the size of the crystal, I start to resolve the underlying structure, and waves that enter that thing now don't see a continuum, they now see these massive objects that are in the way, and it bounces between that and undergoes Bragg scattering. And so I want to propose to you a quantum graph approach to this problem, where we describe both domains, this homogenization domain, this continuous domain, and this discrete domain. And what we should be able to do is describe the discrete domain and reproduce the homogenization results from it. And so what I'm going to do is I'm going to take my system of atoms there, and I'm going to zoom in, and I'm going to define my atom by this object, gamma. Now, you can define gamma any way you like, and naturally, this is a scattering system. I want to throw information at it, I want it to interact with that object, and I want those waves to come back out. And I want to think of the simplest possible system, so the simplest set of equations I can think of are one-dimensional wave equations, and so I introduce these channels, I'm going to call them leads, on the left, right, down, and up, to that object, wherein I can then excite what I call my the wave equation here, which in this case is the Helmholtz wave equation. The word quantum in quantum graph theory typically becomes, because that's a Schrodinger equation, but it can be any wave equation you like. And I decompose the solution to that problem into a vector of solutions on the left, on the right, down, and up, which I express as a linear superposition of counter-propagating plane waves. So this wave have these amplitudes on the left, right, down, and up have an index plus, and that means that they're moving out from the atom. Likewise, associated with those outgoing waves are a system of ingoing waves, which have an index minus, which tells you that the waves are going in. And what that allows me to do is then express the system of outgoing waves in terms of the ingoing waves. And I say that the relationship between those two things are a scattering matrix which depends on the object that I put here. So I'm now going to try and work on the board and explain how we construct these scattering matrices. So if I press that, that should turn off. Okay, good. And I can then explain to you how to construct those scattering matrices. So the problem is I have a set of solutions on the left, right, down, and up, which are outgoing, and those are related to the set of solutions which are ingoing to my atoms on the right, on the left, right, down, and up, owing to some scattering matrix which depends on the chosen object that I've put in my vertex. In this instance, this is a forward image. So it's a framework solution, so it's single frequencies.
It's 2D,
It's a 2D problem, right? But it's represented as a system of one-dimensional. KZ, yes, yeah. So okay. But I can put into that solution that this is, I have my set of directions, and I can call this Z on the right, Z on the left, Z going down, and Z going up. And you can express all of the directions there in terms of the different directions. Now I've not put in X and Y as my evolving term, because then you get an impression that the deductionality. But of course, all of the dynamics are just local dynamics. Okay, so I just say Z. It could be any. That's a lovely point. Yeah. You could do it in 1 dimension, 2 dimensions, or 3 dimensions, n dimensions. Okay. But regardless of whether I do it in n dimensions or not, we say that the relationship between all of those ingoing waves are related to all of those outgoing waves, owing to a scattering matrix. Yeah.
Okay, so does that mean there's an extension to
Yes, yeah, of course. The only thing that changes is the length of the vectors.
Or if we want to do like lattice instead of square.
Yeah, any lattice you can think of, any object you can think of, just introduce my directionality as the relationship between the atoms. The honeycomb is pointed.
So with that, so the number of directions is the number of
yeah. But as
notion of nearest neighbor property means only that there is an edge, but there is an edge is similar.
That's right. But of course, I've chosen it to be square periodic, but maybe you have a different structure in mind, and so I encourage you to be not square periodic. Okay, so regardless, there are ingoing waves in any dimensional space, and there are outgoing waves. And I want to describe a resonant structure here, and I have to think carefully about how those waves are coupled to each other. And so let me think of just an example here. I'm going to think of a very simple example of a graph constructed at one edge. So here's my different directions. Let's say this is the left, this is right, this is down, and this is up. That's orthographic view. And I'm going to introduce an additional length here, which I represent as my resonator. Okay? This has a singular length, let's call it L1. I don't mind. And I'm then going to say, how do I construct the relationship that takes the waves as they come in and maps them to the waves that come out purely on your mesh? Okay? So the first thing you can take into account if you want to construct a gamma is the waves that come in on these, let's call them leads. So I'm going to say, using leads as the symbol L, Z is exists between 0 and infinity. So they're infinitely long, let's say. It's just an isolated system. I'm not thinking about any atoms, I'm just thinking about some scattering sites. And I'm going to say that the first dynamic to take into account is the wave that comes in is mapped onto the neighboring leads owing to the scattering matrix S, L, L. That's that scattering matrix that will lead to the lead. And the next condition to think about is then that wave can then come from the leads onto the graph, in which case I then say that there must be a scattering matrix that couples me from the leads to the graph. And once I'm on the graph, I can then undergo some propagation which takes account of this length L1. And so what you then get is a propagation matrix P, which is a function of L1 and let's say K and L1, where P is defined to be e to the I K L1 0, 1, 1, 0. It's two-dimensional because you can go up and down. So then this is my propagation matrix, and then once I've undergone that, I then undergo a scattering again, another propagation, another scattering, another propagation, another scattering, and you can get set in this graph, which we can then represent as a series which runs between n is equal to 0 and infinity of both propagations, K, L1, and then the scattering matrices that describe the coupling purely on the graph. So now you've got this sort of bouncing term on the inside, right? So finally, once I've undergone all of my propagations, I then get that wave to come back out, and I've now taken into account all the possible dynamics inside of that graph with a scattering matrix S from the graph to the lead. Quite good. Yeah, that's right. Yeah. You may be a little bit worried and say, okay, well, you've got this infinite series, that's a bit frustrating. But actually, you can express that infinite series as a Neumann series, and it leaves you with this expression that the scattering takes account of the prompt reflections and transmissions times the coupling term between the graph and the leads times this infinite series which we express as a Neumann series. L1, yes, graph, to the minus 1 P, K, L1, S, graph to leads. And so now all of that scattering dynamics is now expressed in a closed form, where the dimensions of this matrix here, which I have to invert, is just equal to twice the number of graph edges here. And so that is true for any structure. So I can then think of some very strange structure where I then introduce maybe a loop here and some other things like this. Maybe this is your resonator. I don't know what property it is that you'd be looking for, but that resonator design is taking account of in that expression which is given in a closed form. And the elements of the scattering matrices just take into account the boundary conditions that I associated with each vertex. So you may say I have Neumann boundary conditions and just substitute that in, and you have a scattering matrix.
So you only attach this resonator so one way.
The same formula can be used, and that's a good point. If I want to then divorce the leads from each other, I can then introduce, and I will introduce, a structure like this, where I say, okay, the wave that comes in here, if it wants to get to the other side, it has to then undergo some length change. Let's call this Lx over 2, Lx over 2. And then if I want to go north to south or from down to up, I then undergo some other Ly over 2, Ly over 2, something like that.
So that principle you can put any graph you want if you single out 4 boundary.
That's right.
Very complicated.
Yep, you can make it as complicated as you want. And all that happens is you introduce more and more edges, you increase the size of the parameter space, and the number of variables you can play with to give interesting wave effects. So this is a very simple example, but if I introduce this system, I then get a scattering matrix of my graph, where this green and yellow defines my graph, which depends on my frequency term, and it's implicitly a function of L, X, and L, Y. Okay? So just to...
Can I be really thin?
Of course.
So can you just tell me what the graph is? Is that the resonator at that side?
Yeah. That's the resonator, just add a sign. That's my resonator structure.
And the leads is the link between that and the neighbouring.
That's exactly right. Exactly right.
So when you've got the summation there, what's that for?
So the summation comes from, if I've entered into my graph, and now in this resonator, I then have this infinite number of trajectories bouncing around on the inside. No, within the resonator itself, there's an infinite number of trajectories inside of there. And then once it's quite happy, it increases. So you have You get lower trajectories, and these coupling terms either side that couple you from the graph.
So that summation represents what you might call
Yeah, it's a component of the team.
Is it also to set a learning map and this resonator? You take, you say data is attached for the attachment solid, take learning data.
It may be, yeah, I'm not sure.
It's all possible paths.
Yeah, the trajectories, I think. Okay. It's a different topic. There's a paper I wrote with Sven Grutzmann, which is in submission at the moment, of dealing with this problem. Yeah. You just have to be careful with the coupling terms. That's all. So we can, yeah. It's a different topic. It is invertible. It is, as you say, very poorly behaved, and it has divergent solutions. But if you evaluate it at this term, you don't couple to a region of the graph. They're called scars, and then you couple to another solution. And again, you do have the scattering solutions for that. Okay, everyone happy? Okay, so I say there's an atom. It has some resonant characteristics, and you can describe it with this equation. Okay, so
this square bracket exactly goes up, right? One of the capital
at the resonance, right? Yes. Okay, so as Peter pointed out there, this is the band gaps of the structure. But we'll come back. So I'm going to try there we go. Okay, lovely. So think of this resonator. Keep it in mind that I've just introduced some two parameters just to play with and for illustrative purposes. You know, don't need to take it too seriously.
Just to complete with this background discussion, so it can be made more complicated, right? And this
as complicated as well.
Right? Moreover, it could be even continualized, right? Because what we are talking is a discrete version of similar model, continuum models, right? Which is not absolutely proper to the image.
Yes, yeah.
But you have a like
that's right.
inclusion,
that's right.
resonating inclusion,
Yep,
right?
that's right.
Theoretically replicate
That's right.
and again have to know what I'm talking about, right?
Okay. That's right. That's right. And that will open up a band diagram, which we'll see. All right. So back to where we were. There is a scattering matrix. You can define it in a closed form with some structure. It's up to you. And I said, okay, think of this one here, which has an Lx and Ly parameter. I substitute that in, and this is the scattering matrix I get, where I have an Lx dependence, I have an Ly dependence, and all of the trajectories on the inside are taken into account by that matrix. Okay? So that's how I describe an atom. There's a graph, it has trajectories in it, I solve it in the closed form, and now I want to plug those atoms into my mesh, which again, I've chosen to be square periodic. You may choose it to be triangularly periodic, anything you like. And so I'm going to take my system of atoms here, and I'm going to relate them to each other in this grid. Now, of course, all of the dynamics that happens on the inside of this structure can be thought of as just a single vertex, where that vertex contains all of the information of that scattering. So we're now sort of back to simple periodic structures where I have some non-trivial boundary conditions, some frequency-dependent boundary conditions. Okay? And if I now want to understand the wave transport through the system, I have to take into account three dynamics. The first is, of course, when the wave goes into the vertex, it comes back out, and is governed by the scattering matrix, which we just covered. The next is, as a wave moves from one vertex to the next vertex, it accumulates a phase e to the ikl. You can see them here, e to the ikl. And then I introduce this periodicity condition into it, to say that the waves that travel from one unit cell to the next unit cell are equivalent. They must be the same. It's a periodic structure. If I know the solutions at location 0, 0, I know the solutions everywhere. And if I want to match those solutions together, I just introduce these phase terms, which I've called e to the I kappa xl and e to the I kappa yl, where kappa x and kappa y are my quasi wave vectors, my block wave vectors, that describe wave propagation through this periodic structure. So it's lowercase k, which we think of as a frequency term, and then I have this k, kappa x and kappa y, which moves you through your structure. Okay? So let's think of a very simple example. So this is my secular equation that comes from that condition of periodicity, phase matching, and scattering. And I'm going to plug in my resonator, and I'm just going to say Lx and Ly are equal to 0. So these just then couple back together, and I have my standard Neumann boundary condition. Nothing particularly interesting. And so if I determine that, I get out some band diagram, and I can say, okay, take a single k value, single, let's say, frequency, and pick a value of kappa x and kappa y, and you can solve the Helmholtz wave equation with that information. And what you get out is this plane wave now moving through your mesh. So it's a bit strange that you get this sort of two-dimensional wave dynamics coming from a system of one-dimensional lines. But remember, the system of one-dimensional wave equations are embedded in a 2D real space. So the phase space is continuous, but the real space is discrete. So you get out quite an surprising to me at least, effect of continuum in some sense. And so then I think, okay, how can I illustrate what it is that we've done? Is I can sort of imagine if I just superimpose all of the solutions together, I add them all up with some time dependence, and what we get out is then a model that I can sort of hit. I can now hit the graph, the metamaterial, and you can see that the wave transport through the system is now a function of my chosen scattering matrix. If I change my scattering matrix, naturally I change the wave transport. So now you have a sort of nice engineering tool to say, okay, I would like to now engineer the waves to do something non-trivial, and all I have to do is now play with my parameter space that constructs my scattering matrices, and now I can choose the direction of energy flow within the graph, within my metamaterial. Okay. All right. So what I want to do is say, okay, how do I sort of inspect these models? How do I inspect my material? Typically, we shine sort of beams or lasers into them, and we see what happens as they bounce around on the inside. And so what I want to do is then use my eigenfunction basis to construct Gaussian beams.
Here's some discussion about the direction.
Yeah.
But
So you're asking the amplitude seems higher here than here.
right there.
That's a consequence of the square periodicity. Yeah. As I move lower in frequency, maybe I go back to this diagram here. If I'm in this low frequency regime, I have my Dirac cone. Solutions are so convenient. But as I move up, I start to see the underlying square periodic structure of the graph, and that starts to bend and retard the waves in a given direction. And so what we get is, if I go at 45 degrees, I still have real solutions, but if I go straight left or right, down or up, I have imaginary solutions. Right? And that's a consequence of the square periodicity. And so you're quite right to say, actually, I notice that that is present here. So that depends on the frequency regime. But as I move into higher and higher frequencies, I start to resolve the underlying graph. Okay, lovely. Okay. I want to construct beams from these solutions, and so I have this integral to perform where I say, okay, here's my system of basis functions. These are the block modes of my graph, and associated with each of them is some Fourier coefficient, which I can choose arbitrarily. And so I've animated this to say, okay, consider a single frequency of my domain. Here's kappa x, here's kappa y. And I say, okay, associated with that sort of ocean of solutions that I'm allowed, I associate some Fourier coefficient. I've chosen it to be Gaussian. And I see that the width of that Gaussian is a function of the number of solutions that I take into account. So the broader that Gaussian, the broader the number of solutions I get. And the result of performing that multiplication of this term onto this term and integrating over the space gives you your Gaussian beam as a function of the width of the Gaussian coefficient, right? And so then we say, okay, I now have decided on a Gaussian width that I'm happy with. I can then just move the center of that Gaussian beam, and I can now rotate the beam within the graph. So now you have a sort of probing tool to learn about your metamaterials, okay? And all you have to do is integrate over your eigenfunction basis.
Doesn't it spread to the packet?
Sorry?
The wave packet doesn't it spread?
The wave packet spreads, yeah. Okay. So what I want to do is now explain how I can vary this parameter space in Lx and Ly, and we'll just sort of see how those effects change this wave propagation. So consider the following. I say, okay, on the left-hand side, I'm going to introduce one metamaterial, which has one scattering matrix. And on the right-hand side, I'm going to introduce this other metamaterial, which has a different scattering matrix. Okay, so if I take, let's say, metamaterial 1 to have standard Neumann boundary conditions, this is for Lx and Ly equal to 0, so there's no phase modulation as the wave goes across a resonator. And then on the other side, I think something a bit more interesting, I introduce this scattering matrix again, where the parameters Lx and Ly are free to play with. And at the moment, I've set Lx and Ly equal to 0 times L. And so at the moment, the wave just travels across as if there's no bound. They're equivalent systems. What I'm going to do is I'm going to vary the wave dynamics in the y direction, not in the x direction. And what you'll see is that the wave then meets its interface and begins to bend as it moves from one material to another material. And you get a kind of Snell's law effect coming in here. Naturally, I can keep playing with that parameter more and more and more. And what happens is that the allowed bands, the real solutions then disappear, and the allowed solutions then exist in the imaginary domain. The physical interpretation of that is evanescently growing terms, evanescently dying terms. I remove the evanescently growing terms because they violate some of the radiation condition. And what I have is total internal reflection. The wave comes in, it meets the interface, and it goes back. That's right, that's right. Yeah, yeah. But it's now formulated on graphs as a function of this parameter space. Okay, so I can just keep going and keep playing with these parameters again and again and again. And what you see is that I can then excite very non-trivial effects here. And so there is now a construction of the meta-atom, or this resonator, which has a phase modulation inside of it that produces negative refraction within a frequency limit. Okay, so this is as I say, quite a trivial formalism. You can extend it to n layered metamaterials, and I can start to layer more and more metamaterials again and again and again. And so I've actually gone a lot quicker through it than I thought I would, but this is a set of conclusions which we can get from it. So this square periodic quantum graph construction made out of these point scatterers can be used as a paradigm for a metamaterial, and from those solutions as a basis, we can construct different wave sources. In this case, we have a Gaussian wave packet, and then we can do exactly the same thing for a Gaussian beam in a given direction. So what you get is then these sort of Snell's law effects at interfaces between them. And if I use the transfer matrix method, I can then just layer these materials one after the other, and we can start to get some kind of beam steering effect.
This is like a different refraction, right?
Yeah, yeah, that's right. Yeah, yeah, that's right, that's right. Okay, there they are. I got through it a lot quicker than I thought I would. Thanks very much.
Let's have questions. Who's first?
Hello. Yeah.
So, that's actually very interesting to see what side you are. Are there no small bounds?
Not in this structure. There are domains. Good question. Good question. Oh, I'll have to blank this again. Is that right? Okay. Now, example. If I look at it from side on, here's my capital X, and my capital Y coming out of the board. And here's my frequency term. This function of capital X and capital Y. I have my Dirac cone in the low frequency regime, and as I move up, you get this effect. Okay. Okay. And what you get in that domain is that there's this region here with no real solutions. And this couples to imaginary solutions. And if I look at this from top down for a frequency here, what you get is where the domain of solutions is like this. So I can consider an interface with circularly distributed frequency here, an isofrequency contour, this interesting contour effect here. And what you get for modes for wave vectors, the low wave vectors, is a stop band that I cannot couple between your solutions. Sorry. It's a periodic structure. So the solutions that you have over this Brownian zone then flip into the next Brownian zone. That's right.
Can I ask about terminology? Why do you call this a hierarchical code, right? This local together, yeah.
Where it's
something hierarchical is a different subtle effect normally, but very special configurations, right?
I'm not so sure.
It can happen at any time. But this is the kind of usual kind of local behavior, yeah. European optimization and the services and interactive services the problem that we need is because there's better parameters versus this quadratic, right? So quadratic point. Not, but if it takes square root, right, of lambda, which is frequency, and that is conical, and you can call it the same as what we know under other names. So here you should observe slow propagation probably.
Yeah.
So instead of stop to the right,
slow
slowing down. Okay, so this is I have a question. How could you show an example how complicated those structures you have to put into vertex example to get your effect?
Oh, I just used
An
this.
example.
Yeah, I just used this structure as before, where I said
You only play these lines.
Yeah.
Wow.
this could change.
What is
Okay. Maybe I'm on the pre-option space. I have my mesh within the structure. So this is the next unit cell, right? Okay, and it's same everywhere. And if I want to modulate the wave as it goes from this edge to this one. Okay. And so all I have to do is just introduce some structure there that modulates the phase. Okay? And I thought, what's the simplest structure I can think of which modulates the phase in one direction differently from the wave that modulates in another direction? If I choose the structure to be joined at the same vertex, then you can't break the symmetry. But if I choose to dislocate them from each other, then you can break the symmetry. And so what I say, okay, I want this wave as it goes from here to here, just to accumulate an additional phase, e to the I k Lx. And I want the wave as it goes from here to here to accumulate additional phase, e to the I k L1. Now you have these two parameters, and to connect them, I just put a vertex there. Yeah, pick up number of. So what this means is that the wave that travels in the mesh should be traveling a distance L as it moves from one unit cell to another. But actually, it's traveling a distance L plus Lx plus Ly, but it is not aware of this dynamics. So you can consider resonant effects, which I know Peter's looked into greatly, but you can also do the same thing by adjusting, attenuating the phase as you move through this.
What makes that we have a very nice picture in the beginning, but do not read inclusions and no need to redisplay, right?
Okay.
In the memory, right? But you know what I mean? Do not inclusions on the right homogenization, usually low frequencies, and then intrinsically more kind of prominent and very sharp on the left.
Yep.
Nice illustration, right? That this kind of resonance type effect starts showing up with higher frequencies that is supported by this low.
That's right. Yep.
But on the other hand, anything, you can make a hybrid of like give some homogenization still on the board, and but which inject resonant effect already. In continuum model, there is one high contrast model, right? Or sub-wavelength resonate, right? It works for the same thing, right? Probably you could find something like that in your quantum graph model, right? You have square lattice, low resonators yet, but you are still considering a low frequency wave propagation, therefore you are entitled homogenized, and then you put on the top of it, you need to pick up parameters, right, some resonators, which resonates at this low frequencies, which are still homogenization pattern that allows to detect sort of kind of effects in a more explicit asymptotic way.
Yeah. I think to add to what you're saying, I think you can construct the continuum solutions from the discrete model. So if I take maybe I have it here. Okay, so if I take that equation here, which says takes into account the phase, periodicity, and the scattering, and I substitute in this standard Neumann boundary conditions of the vertex, this has an analytic solution.
It's essentially a continuum solution with the discrete resonators on the top of the right side. The continuum discrete model, right? Which is a legitimate asymptotic right?
Yeah. But I'll just say that this has an analytic solution which is given quite standard. This. So that's our dispersion diagram, which relates k, kappa x, and kappa y. And if you take the limit as those edge lengths between resonators tend to 0, and you do the Taylor expansion there, you end up with a factor 2k squared to kappa x squared plus kappa y squared. So we're a factor of 2 off of the true free space solutions. Okay, but I think you could just do a bit of rescaling and say there's a graph refractive index such that I say, I don't know, and then use that in your differential equation, and then you do have a continuous model. And of course, I can introduce S, you bring on trivial S, you could do the same thing, and you can reproduce the dispersion diagrams in the continuum as well.
Continuous model as an honest and a homogenized unit, right?
That's right.
The homogenization is special. It's the usual homogenization, only needs the lowest frequency.
Yeah, not actually there's what they call micro-resonant.
That's right.
Resonators to get too much homogeneity, but they reflect visible numbers.
Sure.
Homogenized properties, right? And in a visible way.
I saw a little bit at the beginning, probably the main one, showed some images, and I thought, well, I know this stuff. And then the model wasn't put together.
Right. Okay.
I think that's we got in the end, but just tell me, practical realization for your metamaterial. What do you have in mind?
Oh, well, I don't want to talk about something I'm currently working on, because we have some results on it. But I think you can think.
Put it in terms
Sure.
of things that we can't all go
You
on.
can
Steal your ideas.
No. If you think of a set of pins, okay, so a structure like this, you can think of that as a plate with a nail in it. Okay, where the length of the nail modulates the phases it goes between.
There you resonate.
That's a resonance. Yeah. This is the model. Now, if you
It's even easier. In fact, you don't put any resonators there. What you do, you can take your edge and make it of 2 different materials.
Yeah.
There is no resonators there. Just the edge. When this is that way, if you combine 2 different materials, that's it.
But this is one loop, right? This is
Sure, but
one
it
big
extends.
substrate picture.
I mean, this picture. So
This
if
one
you
over
look,
here.
if you pull it, it will be flat. You will see the square lattice. So what actually happens, you make your wire of 2 different materials. This is one material, this is another, let's say.
But what's the matrix under there? The waves being carried on beneath the resonators. Is it truly 1D? And I think this is getting back to what King asked at the beginning.
That is the model of quantum graph, where those
You have your base material, you put some resonators on it, and you turn it into a metamaterial. Okay? I'm saying, what was that original material applying it before we
Microelectronics, I first time quantum wires, and instead of solving Schrödinger equation in extremely same areas, we try to take the limit.
Okay, but that puts me on more solid ground that I'm no longer an application.
I'd say to make this point, if you introduce these pins into a plate and you vary the height of those as a function of position, you can construct cloaking effects, for example.
But sure, yeah, I mean, people have done things like this.
Yeah.
The plate is quite different from the leads.
The important thing is that
this is
that's true.
The model that you're proposing here, and
that's
the
right.
ones that most of us would usually do.
Yeah, but the important information in a long wavelength regime is the relationship between the resonances. And so the information transfer between them is quite trivial. And so it can be modeled trivially. As you take the limit as everything comes together, you restore the two-dimensional dynamics of the plate. That's what this says, right? So here's my dissipative properties of my plate. That comes from a discrete system. So I restore the continuum solutions from my discrete system.
But what if you have to say monofold resonance? Three-dimensional, it's monofold. Is it then appropriate to put in the plane where it's
The key information is what is it that is coming from one resonator to another resonator. And if you think in a long enough wavelength regime, the dynamic of going here to here is the dynamic of going here to here. So you, in a sense, in this continuum, you restore the two-dimensional equations from a system of one-dimensional equations.
So not to be clear about practical things, the origins. So we can take advantage of explicit quantum graphs. So it comes from quantum mechanics, right? The original equation, like through multi-dimensional Schrödinger, right? But something structured, I think you said, right? We need to take us to the limit, right? And
It's not always works,
quantum
depending on what is done to it, on this wire. Some mathematically, if you wire, if you restrict propagations of the wire by normal conditions, you can take the limit to get such that is. If it's Dirichlet, then it seems to become very complicated. So it's already.
Some people still manage to make progress for Dirichlet, but
Yeah, we're sort of dominating the discussion
There's a
here.
question
I
here.
want to look behind me and see if anyone else wants to say anything. Ben, is that your hand up there?
So, you've got this fully correct
Yep.
the really way you can do all of this is just think about the
Oh, okay. That's a good question. Yeah. So the dimension 4 is just a consequence of the number of dimensions we're working in, right? So it's 2 times the number of dimensions. Okay. So in higher dimensions, you have more coefficients to take into account. Okay. But the question of whether or not there's a restriction on the kind of scattering matrices you put in there is a nice question, because we want to say 2 things. One is that, let's say that this condition must be maintained. So in the context of this conjugate transpose of the scattering matrix acting on itself, if it's identity, that means all of the energy that went in came out. Okay, but if it's subunitary, that means that there's a damping on the inside of the system, and you can model that with a complex term on the inside. And that means that not all of the information that comes out, not all of the information that went in comes out. And that's allowed in there too, so you can take into account that also. So you can think of that as gain. Yeah, you could model that if you wanted with an additional lead input into the graph, something like this, where information can then come in and interact with the system. That would be super unitary, more than unitary. Yeah.
More questions?
Yeah.
If you would like to incorporate a larger staker, how would you proceed? Can you incorporate that in a non-finite portal, or you replace your staker by some?
Yeah. So I've thought about this for the context of rough surfaces. You can construct the solutions to reflections at a boundary, where you might think of a half space. I'm not interested in any of this, and then I want to create some rough surface, and I may want to know what the reflection coefficient for that object is. You can decompose that into a graph structure. Something like this, and then attach this to the remaining mesh. But this is then square root. So this is my sort of free space Neumann graph, which is discretized, and then you can couple that and generate the reflection coefficients for a rough surface. And I imagine the same is true if I wanted to construct some rough object. I would then superimpose my mesh over the top of it, and then I would pick vertices that make up this object that are reflected, something like that.
How do you find the low from the resonant part?
How do I find the?
Not the low, but the design of the resonant part.
How do I find the design?
I mean, this kind of the length of the length here or the length of the resonant.
Yep.
You shoot that at that point.
Oh, you can. So if I, for example, I wanted a reflective boundary, so I had, let's say my rough surface, everything was Dirichlet boundary conditions. You can just introduce Dirichlet boundary conditions onto these.
That's incorporated with the shape of the boundary.
That's true. But that's taken into account in how the incident wave, which is a single eigenfunction mode, is coupled to the reflection field, which is an integral over the full set of eigenfunction species. And that reflection coefficient that you generate from that integral is a function of the topology that you choose as your work surface.
Yes.
That's right. Yep. I think so. Yeah. I'm not sure. What do you think it is? Yeah. I would have to write it down, but.
So here's a page that you can have now.
Yeah, I think I'd have to think about it. Yeah.
You don't have this page.
No.
Any more questions? One question: why quantum graphs?
Why quantum graphs?
Since I think that the same thing should work for discrete ones. I don't see actually where the quantum graph involves PDEs, differential equations on edges. Why not here?
The
I
edges.
think the same thing should work for discrete equations.
Each edge is endowed with a differential equation, and the relationship between them satisfy the boundary conditions. That's the quantum graph construction.
Yeah, but you can replace this just by transmission. Or
It has an end.
Depends on K, right?
Yeah. It has a K dependence. That's right. Yeah.
Are you saying this could be acoustic? Given the purposes of
Exactly. Yeah.
one-dimensional acoustics along the leads.
That's right. Yeah.
Need and
That's fine. It's only quantum in name.
yeah.
You feel free to endow any wave equation you like into the system.
Right.
The formulation is.
And the key is you have these waves which are exponentials and
That's right. Your interpretation behind the oscillations is really up to you. I'm not going to enforce it onto you.
quantum graph is
Wavy graph, something like that. Yeah.
With your system, you have some exponential term.
Sorry, say again.
For example, not sending the wave, but
Oh, yeah.
source down, you can have a function decaying wave.
That's right.
What we want to show are not taking into account. You could incorporate that in the model, or
Yes, yeah, that's true.
can you elaborate?
How to introduce this additional parameter in there? That of a imaginary wave component?
At the interface, we expect exponential decay in the part in the region where the wave can go through. It doesn't occur here because in the model, it can be there. Can we enrich the model to take that?
The solutions that come across the interface are imaginary. Maybe you're asking a different question.
For the continuous material corresponding to this thing, you set the wave, then wave, then wave. We have the part which will decay in the solution in the graph. And here it doesn't decay because you make a simple model. You get a more complex model, so that you have this makes sense.
It just doesn't go into the it is there. There is uniqueness of continuation, which, for instance, a continuous model doesn't allow it just to stop. So there are elements.
Yeah, I should. Yeah, sorry. I should elaborate on that. That if you have your solutions here, which is circularly distributed in one, it's kind of circularly distributed, and then I have this hyperbolic region. The solutions for this chosen value of ky are real incident and reflected waves. But if you want to find the solutions, you do not look in the real space, you look in the imaginary space. In which case I consider the solutions in here, for which kappa x is imaginary. And then you have here these evanescently dying, evanescently growing solutions, and I couple this here, and the result is that the waves evanescently decay very aggressively in this case, as they move into the return.
Okay, this else has a question. John, I think we should thank Tristan again for a really interesting talk.